instead what I'm going to do is to use a slightly different definition. Yeah, I'm going to actually use the other. So instead, what I'm going to do is to say the following. So we know how to get this. If I add to the right a linear operator, then this thing must be a bra, because why do I know that? Because it can act on a cat to produce a number, a complex number. Remember, that's the goal. That's the purpose of a graph, right? It's something belonging to the dual space in such a way that it can act on the cat to produce a number, right? And so, for example, if I take alpha x acting on the beta, then by associativity, I can say that this is alpha, and then x acting on beta. That's a cat, right? But alpha will then act on this cat, and this will give you a complex number. Right? So at least it behaves like a graph, in the sense that, and you can check all the linearities and all the properties that we talked about before, how this thing will act, how graphs act on cats, right? All the definitions of the inner product will not change even after you insert the x. Okay. So what I'm going to do is I'm going to define this to be, in fact, x dagger acting on alpha dagger. Okay. So we'll see that this definition is going to turn out to be the same as the definition that I wrote down before. And the reason why I do this is kind of more psychological than anything, because of what I just said. I know how to carry out this operation, right? If you give me any vector, I can act x on it if I assume I know what x is. Then, because I don't know x dagger, but I know x, so I can in fact, always act x on whatever vector you give me, and then followed by acting alpha graph on the result. Okay, so this I can always do. And because I can always do this, I can figure out basically what the action of this guy is on any vector. Okay, I can figure out this action. So now it makes sense to say, okay, if I can figure out what this is, then I can hopefully figure out how to construct the corresponding cat. Okay, I can hopefully figure out how to construct the corresponding cat, so that when I take this adjoint, when I take this dagger, I will produce the bra that will do the job for me. Okay. So that's the starting point. we'll see that another way to think, so this might be a little bit abstract, but the way to think about it is also to simply say that this is the equivalent to saying that for any alpha and beta, if I take the complex conjugate, so now this is a number. Okay, so why is this a number? Because let me just start from here. So this is acting on beta and gives you a cat, and then alpha bra acting on the cat will now give you a number, right? So this is a number. And so I can certainly take its adjoint, its complex number, complex conjugate, I mean. And what it means here, there are two ways to think about this. So this is now a complex conjugate of alpha beta prime, where beta prime is just x acting on beta. Okay. And of course, you know what this is. This is just beta prime alpha. That's the rule of inner products. You're supposed to just, you're just supposed to swap them. But what is beta prime is actually the adjoint of x acting on beta alpha. Okay. This, remember, is given by this, and beta bra is just the adjoint. And so this is where the definition comes from. This is exactly where, if I can show that there's a relationship between x and its adjoint, you'll find that this is exactly beta x dagger alpha. Okay. And later on we'll discover that, in fact, x dagger is x, and so so if I swap these guys, right? If I plug in x equals to x dagger, at this point you get back. So I should emphasize, I'm not exerting. This is not a proof, right? I'm just saying where we're going in terms of in terms of where in terms of where we're going. I'm just telling you where the content of what adjoint means first. But we will prove this systematically. Okay? So what we're going to do is we're going to, in fact, leave this definitions and these partial results for the moment. And what we're going to do, because what we're going to do is we're going to actually show you what the adjoint really is by explicit construction, right? So here you have to bear with me a little bit. I'm telling you what the adjoint means, so you can either define it in this way, or you can define it in, like I said, as x alpha adjoint. Either way is fine, but to actually, so it's a little bit abstract, but to actually construct the adjoint will take a little bit of effort. Okay, so you have to bear with me a little bit. And after that, the construction, you'll be able to see explicitly that this is true and all of that is true. But any questions for me at this point? guys seen this before? When you take an undergraduate course in quantum mechanics, have you guys seen this before? No? Yes? Okay. Who has seen this before? About half, is that right? About half of you. Okay. Yeah, that's why I do this, right? Because I realize that not everyone has seen this, and it is quite crucial in the formulation of quantum mechanics. Okay, so please stop me if you have any questions. So what happens when you take the adjoint of, so with this definition, you already can show the following. When you multiply two or more linear operators, what do you get? You get y adjoint and x adjoint, right? So you should remember, this is exactly what you do when you multiply matrices, right? So for example, when you have two matrices, and you find, let's say, the transpose, you can imagine that they're real or complex, actually, doesn't matter. And this will become y transpose times x transpose, if you remember your matrix algebra. So, and then if you are dealing with adjoints, there's also a matrix adjoint. It's very similar. And you discover that actually these guys come from this, at least the adjoint part comes from the linear operator version. Okay. The next thing is, of course, eigenvectors and eigenvalues. So we will soon see that the concept of eigenvalues and eigenvectors are absolutely crucial to the formulation of quantum mechanics. Right. So quantum mechanics is basically about, very much about, firstly what the Hamiltonian is, and also what the observables are. And I'll say this again when we come to Hermitian operators, but Hermitian operators are what correspond to many of the observables in our quantum system. And in particular, it's important because the eigenvalues are the outcomes of experiments for Hermitian operators, and the eigenstates are correspond to the physical state that our system is in, right? And so, so what is an eigenvector? If I have a linear operator, it doesn't have to be Hermitian, but if I have a Hermitian operator, and if this is an eigenvector of this guy, then when it acts on A, it will produce A times A. So this is a label, essentially, for its eigenvalue. So this is the eigenvalue. And the cat itself, is eigenvector. Maybe this is a bit confusing. Let me just say this. Our A is an eigenvalue and the cat is an eigenvector. Okay. And so, in fact, whenever it is appropriate, that's what I will do. I will label my cats using the eigenvalue, and not use some arbitrary alpha or whatever, right? Whenever there's an eigenvalue associated with my cat, I will use that to label my eigenstate, my cat. So I want to say that the eigenvectors are not unique. And this is a slight problem in quantum mechanics in the following sense, right? So what do I mean by that? If I have alpha A as my eigenstate, let me just say, let me multiply A by any number, right? So this C times A is not the same as A, right? It's a multiple of it, but it's not the same thing. But if I do this, what happens is that by the rule of linear operators, right, the fact that this is a linear operator means I can say, I can pull out the complex number, and X will be acting on A, and then it will just give me this times this. I can just use A multiplied by CA. So even though I multiply by a number, it's still going to return me the same vector, C times A, multiplied by the eigenvalue. Right? So I'm obliged, if this is my definition, this is an eigenvector as well, corresponding to the same eigenvalue. As above here. So in that sense, it's not unique, right? If you label your eigenvector by the eigenvalue, it's not unique. And so in quantum mechanics, as you probably know, we usually normalize our states to 1. What does that mean? You have A equals to 1. Why? Because it might be a physical state, right? And if it's a physical state, the probability of finding the physical state in itself is 1, right? Well, I'll talk more about this when we talk about the Born group. But that's usually how we do it. And also for computational reasons, we want an orthonormal set. So if A is part of your part of your basis, which will often be the case, I'll talk about it very soon, we will also normalize it to 1 for that reason. But even then, there's still an ambiguity, right? So even then, let's see, if I take A, but multiply it by a face, so delta is real. If I multiply it by a face, it will still preserve this, right? So why? Because let me call this A comma delta. Okay, just to show you that it will give you exactly the same normalization. So let me calculate A. Oops, I keep writing alpha. You know, A is alpha, right? In Greek, is the same. So A delta. Well, what is that? This is the adjoint of e to the I delta A. Okay, acting on e to the I delta A. And what is that? So remember that when you have a complex number times a ket, this will give you a complex conjugate of this guy, which is e to the minus I delta, which is delta is real, and then e to the I delta A. So these guys actually cancel out and give you 1, and A is 1. So therefore this whole thing is 1. So I can normalize it to 1, but there's always an ambiguity. Okay, there's always an ambiguity. Let me just say it over here. Even after normalizing to 1, there is a always a phase ambiguity. In the eigenstate. Some x. Okay. You cannot pin it down completely. It's always a phase. There was always a phase problem. Any questions for me? No? Okay. So now we're gonna start to make some progress. Let me just see. Let me check my time. We're gonna make some progress in returning to this issue of how to construct the adjoint. Right. This is a very important point in. Yeah, I'm sorry. I think I forgot to record the first 20 minutes of my lecture today, but I forgot to press the button. But again, just to remind you guys, much of this is in my notes. Right? I might say in lecture, I try to say things in a slightly different way, so that when you read my notes, hopefully it's helpful, but the gist of the content is in my notes. Certainly this part, and then later on maybe later in the semester, I'll start to overlap a bit with what Weinberg is saying, but at least for the this part, it's just in my notes. Maybe I should also mention, this is chapter 4 in Weinberg. So Weinberg goes from history to central force problems, I think, and then he talks about this general stuff. But this is a graduate level class, so I thought I'll first do this stuff before I do the central force problems. It's also the first chapter of Sakurai. So this is the other book that I recommended. And what I'm doing is really an elaboration of what Sakurai has done. I think his discussion is much clearer than Weinberg. Weinberg uses this the math notation, and then he writes in a way that is sometimes a bit too concise, I think. Okay. So the next thing we want to look at is what I like to call the cat-bra operator. And once you understand this, you'll see how basically any linear operators can be constructed out of these cat-bra operators. So that's where we're going, right? So why I'm talking about this is because, again, basically any linear operator I claim can be constructed out of this. But first, what do I mean by that? So let's just write down a general cat-bra operator. So you have a cat, you have a bra. So I claim that this is a linear operator. And by the way, I also claim that this is the reason why the Dirac notation is more useful, is cleaner to write in many cases than the Mach notation. Right? I don't mean to start a war between mathematicians and physicists, but this I claim makes it cleaner. And so why is that so? So I make this claim, and all I have to do is I just have to check that this thing is a linear operator in the sense that I have laid out previously. Right? The first thing is it needs to act. Right? The first thing is it needs to act on any cat and produce another cat. So let's act it on any cat. Right? So alpha, beta, I assume are fixed cats and fixed bra, but gamma is arbitrary. Okay? Well, what does that mean? It means that this I have an alpha, and then multiplied by this complex number that I get from beta acting on gamma. Right? So this is a number. So what I'm showing is that this cat bra operator acting on any vector in your vector space gives you some number that I can compute multiplied by a cat. So that's exactly what linear operators do. Right? It acts on cats, any cat in your system, and returns another cat, maybe multiplied by a number. So it passes the first check. And then we can go on to check linearity. Right? So for example, if I have two of these guys, say C alpha prime beta prime plus D alpha beta. Right? So I have two of these guys, and I act on gamma, it needs to give me, it needs to be linear. So what do I mean by that? It means that I have C, I have now alpha prime, and then beta prime is going to act on gamma. And then beta is going to act on gamma as well. D. Okay? And that's the same, obviously, as C alpha prime, beta prime, acting on gamma. Right? So remember, the sum of the operators acting on this must be the same as each individual operator acting on this sum. And then you can do the same, but now for acting on a superposition of let's say gamma plus gamma prime. Okay. And what is this? This is just it's just distributed. Right? It's just C alpha times C beta gamma plus alpha times D beta gamma prime. And this is of course equals to just alpha beta acting on C gamma plus alpha beta acting on D gamma prime. Okay. Maybe we should take a break. Let's see. Yeah, let's take a 10-minute break, okay? And then we'll return to continue this discussion of cat bra operators. But basically, this shows that cat bra operators are linear operators, and soon we'll see how to use them to construct adjoints. Okay? So see you guys in 10 minutes. All right. So discuss is what is the adjoint of this cat bra operator. In fact, it's a homework problem, but I gave you the answer. So this is the closest to, I think there was a question and I was asked before, what's the adjoint? We know the adjoint of the cat is defined to be a bra. But what about the adjoint of a bra, right? So we're not discussing the adjoint of a bra itself, but here, if you have a cat bra operator, you will discover, you can prove. It's not an assumption, right? It's something that you can prove. This is in fact just the cat bra swapped into bra cat. Yeah, so beta becomes beta cat, and alpha becomes alpha bra. And the way you want to prove this, I won't step through the whole thing, but I do have a bad habit of telling too much in the class, so the homework becomes a bit too easy. But remember that X dagger acting on gamma adjoint is supposed to give me gamma X. Right. So, yeah, so in fact, using this alone, and then you just consider what happens to the right-hand side. Okay. So I shouldn't complete the answer for you, but like I said before, I have a bad habit of giving a bit too much away, and basically I tell you the answer. But let me resist. Okay. And there's a special kind of cat bra operator. It's called projection operator, where both the states are the same, and both the cat and the bra. And why it's called a projection operator is because when you act it on any arbitrary state, this is basically like the dot product between some arbitrary state. This is an analogy, right? I don't mean it to be literal, but this is a projection, right, on the state and in the direction of this alpha. So that's why it's called a projection operator. Again, I don't mean it to be literal. This is just figurative. It's not literal. Right? Remember, you can't. We're talking about complex data products here. Okay. All right. So now, let's turn to writing things in terms of orthonormal basis. Okay, so suppose we have a set of orthonormal bases. What does that mean? It means you take the inner product, you get connector ij. Okay, so this is the definition. And now, what it means is the following. It means that if I take any cat, cat in my vector space, if this is a basis, then it means that I should be able to superpose it over these bases, right? So my hat are numbers. My gamma hat I is the ith coefficient. I'm sorry, this is I. Ith coefficient of the ith basis And I'm just superposing it over the basis that I have. Okay. But I can invert this relation in the sense, in the following sense, I can project J on both sides. So I get J gamma equals to gamma I, J I. But remember that this is orthonormal, so this is Ji as well. Right? If I take the complex conjugate on both sides, this is just 1 or 0, so it's real. So complex conjugate doesn't do anything to it. But Ij will become Ji. So this guy itself is connector Ji, which just means when you sum over I, when I is not equal to J, it's just 0. But when I equals to J, you get 1. Right? And so therefore this will just give you gamma J. And it's just saying that basically when you have an orthogonal basis, it's just very much like doing it in real, the real vector space that you are probably familiar with. All I'm doing is I'm specifying the components of each of the orthonormal bases. And this is just a projection. So what does that mean? It means I can plug this back in and I say gamma is now equals to I. And this number I know now is actually just a projection of I gamma. Right, so this is just a, again, projection of gamma along the I direction. And like I said before, this is the kind of the notational elegance of the direct notation. Right? If you try to write this in the math notation, it's going to be a little bit more messy. And so it's useful in again, I don't mean to be dissing the mathematicians, right? They have their reasons for doing it, I'm sure. But because we write this again and again, this thing will show up again and again. So you'll see that this, in fact, is a very useful way of writing things. Already at this point, there's something that is worth pointing out. Okay, so this is, we seem to be doing something very simple. All we're doing is just projecting the components of a vector along the orthogonal directions. But here, again, using this notation makes it very easy to see. If I sum over all the projection operators associated with my orthonormal basis, and then I acted on an arbitrary vector, right? So I have not assumed anything about gamma. It's just some arbitrary vector in my vector space. What I've shown is that summing over its orthogonal components is the same as taking all the projection operators, sum them all up, then act on this guy. So let's see what we have earlier, right? Remember the identity operator is defined to be the guy that when you act on any vector will return the vector itself. So what this is saying, this result is saying, right? So this result, okay, is telling us is that the sum over all the projection operators in an orthonormal basis, right? Orthonormal is important, but when you construct this this projection operators and sum them over all the bases, you get the identity. Okay, so this is already a non-trivial statement. If you get, and this is usually called the completeness relation. It's called completeness because you need all of them. You need to capture all the bases in your vector space. Make sure it's orthonormal. Then using this projection operator, you can construct the identity. Okay. And this is something that we'll use repeatedly. Okay. Any questions for me at this point? No? All right. So this is the beginning of the connection between linear operators and matrix algebra. So let me just emphasize this before we go on. Yeah, maybe I'll leave this further. So what do I mean by that? So firstly, what we've discovered is that we have discovered how to write down what's called a representation of my vector. Right, so let me just copy it over here. So given a basis, I should emphasize orthonormal basis. We see that if you specify the components, then you have to specify the vector itself, because all I have to do is I take this guy and plug it in, and I get the vector, right? So this is equivalent to specifying gamma completely. Again, once I know this, I know the vector, because I already assume I know the vectors. It's just like if you're in three-dimensional space, if I've already chosen the x-axis, y-axis, and z-axis, then all you have to tell me is, what are the components, and I know what the vector is. So same thing here. The only slightly more complicated aspect of this is these are complex numbers, right? Otherwise, it's basically the same thing. So therefore, I can basically write down. It's not equal, but I can write down. I like to use this notation. This is basically just a component, a column. 1 gamma, 2 gamma, all the way to d gamma. Remember, you have a d-dimensional space here. And sometimes in matrix notation, I'll write it as gamma hat I. Okay, and that's why I put a hat, just to distinguish it from the more abstract vector. Okay, so this is the I component of gamma cat in the basis in the given basis. So of course, when you choose a different basis, these numbers will be different, right? So one has to be a bit careful. You need to know the basis. Otherwise, if you choose a different basis, or if you don't know what the basis is in the first place, then this is ambiguous. And in fact, later on we'll talk about what does happen when you take a different basis. There will be a transformation between them. So immediately from here, you can do the following. So from here, you can immediately figure out what is gamma bra. Right? Because this is just a cat multiplied by a complex number. So gamma bra is just a sum over the complex number times the cat. So if you take the dagger term by term, it just means that, what does it mean? It means that the cat will become a bra, and then you take the complex conjugate of each component, and this will become gamma I. Again, you see the kind of the notational elegance of the direct notation, right? So hopefully it's intuitive enough. So remember, this is basically sum over I acting on gamma, and so this shouldn't surprise you because the sum over I again, it's just an identity. So it cannot be anything else, right? But this is just a consistency check of our calculation, right? That gamma is just, of course, gamma bra, of course, it's just a gamma bra times the identity operator. But you can step through the rules of taking the dagger, and you find you get the same thing. Okay. But this does motivate the following, right? So since this is these guys, these coefficients, we think of them as the components of a common vector. Now, I would associate these coefficients as now the components of a row vector. Okay. Why? Because now we see that. So this is the representation. This is a representation of alpha. It just means that I have found a basis, orthonormal basis, and instead of writing down gamma in an abstract form, I now have a concrete representation of it as a column vector in this basis. Likewise, this is the representation of alpha bra. I'm sorry. Did I say alpha, gamma, right? Nobody complains when I make the boo-boo. Please complain when I write down something strange. Of gamma bra in the basis okay? And so why is all this useful? Because now, for example, if you take an inner product then you can do the calculation in this basis by just projecting this row and dotting it into the column. Okay, oh, and I should say that you notice that this is nothing but, this row is nothing but 1 gamma, 2 gamma, all the way down to d gamma, and then taking the dagger of it. Right, and this is the matrix adjoint. So this is the matrix adjoint because when you take the dagger means, in this case, this is the matrix adjoint, which means transpose plus complex conjugate. Right. So transpose a column, you get a row, and when you take the complex conjugate, all the 1 gamma will become gamma 1, 2 gamma will become gamma 2, all the way to d gamma will become gamma d. Right. And so now we can calculate, for example, what happens when I have alpha gamma. Now I know why I call it gamma because I want it to be different, right? But it's okay. I think you know what I'm saying. So, I mean, if you have alpha instead, then we can step through the whole thing. But let me just write down the answer. But I hope I think it's clear because all I'm doing is I'm swapping all the symbols. So it'll be alpha I, and then alpha will be represented by alpha 1, alpha 2, all the way to alpha d, and then this again is the adjoint, matrix adjoint of 1 alpha all the way to d alpha. Okay. So if I do alpha gamma, now I can use the completeness relation. And I insert in between these guys, so this is what? This is alpha, identity, gamma. Right? Because identity on gamma is just gamma itself. But now, identity is just a sum over alpha I gamma. This is the completeness relation. Okay? And so you see this again and again. What seems very simple at first, it turns out to be very useful. And you will see this repeatedly. But this is exactly this guy here, this guy here. And this is exactly this guy over here. Right? And so I should say this is now alpha hat I star. Right? So this is represented by this. Right? It's the I component of I alpha, but because it's now the adjoint, I need to take the complex conjugate. So again, this is just alpha I star. This is now gamma I. And so I can use the connected delta to write this, so connect the ij, gamma I, and then alpha I j star. And remember, this was actually one of the, if you've done the homework for this part already, this is actually the first example of an inner product that I asked you guys to prove in the homework. And now you see why it's important. And by the way, you can write this as a matrix operation, right? So it's alpha. You view this as a column vector. It's adjoint, matrix adjoint, acting on gamma. So let me just say it again. So the reason why I asked you guys to prove this as one of the examples of the inner product is because, you see, I did not make any assumption about what vector space I'm dealing with. The only assumption I make here is that you have a discrete, finite dimensional vector space, which happens very often when you talk about spin and so on. You'll find that all the finite dimensional vector spaces that you deal with can always, once you have chosen an orthonormal basis, right, I'm not making any other assumptions other than I have a finite dimensional vector space. So once you have a finite dimensional vector space, you'll find that all the calculations you are going to do with it can be reduced to just basically matrix dot products, but in the complex sense. And of course, there's more. There's more. For example, what happens to linear operators themselves? Any questions at this point? Yes.
Alpha is a
Gamma.
is gamma.
Thank you. Yes, please. Sometimes I make typos on the board, so please tell me. Yeah. There's another question. Yeah.
Can you explain the standard again? It's specified in the part of I.
Yeah. So what I mean is that it contains the same amount of information, provided that you have chosen your orthonormal basis. So imagine, let's say you are in three-dimensional space. Okay, let's say I want to describe this room. Then I say that, okay, let me first start by choosing an axis. Of course, natural axis will be in this room, will be X here, Y here, and Z in this direction, right? But once I've chosen the axis, and I tell you, let's say I put the origin over there, then I can just tell you what is the X component, the Y component, and the Z component, and I'll be able to locate any point in this room, right? So this is the more abstract. So that three numbers, X, Y, Z components, are equivalent to specifying a vector in this room. That statement is the analog of this statement here, right? So if I had chosen a basis, then specifying these inner products is like specifying the components of the X component, the Y component, the Z component. Right? So for example, 1 gamma is like the X component. 2 gamma is like the Y component, and so on. Except that now we have D dimensions, right? So I've run out of letters, but these are the components of the vector. So I don't need to tell you the abstract guide. If I know the basis, and I tell you what these numbers are, that's the same as telling you what gamma is. Right? Just like if I tell you what the X, Y, Z components are of a vector, once I have chosen a basis, that is the same as telling you what the vector itself is. Does that answer your question?
Yeah.
Yeah. Good. Any more questions? Yeah, so remember, it will get more abstract, but that's the concept, that we're trying to abstract what you're familiar from vector calculus, but the abstraction will be very, very useful, very important actually, once we start doing some quantum mechanics. Okay, so now, yeah. Yeah.
What do you mean when you use the hat without the superscript?
This one? Yeah. So this hat just means the column itself. 1 alpha all the way to D alpha. Yeah.
So it's a vector.
Yeah, it's a column vector, yeah.
Okay.
So when I take the adjoint, it means I take the transpose, so it becomes a row, and then I have to take the complex conjugate, right? So 1 alpha becomes alpha 1, and then d alpha becomes alpha d. And then I will dot it into this guy.
So it's a dot product.
That's right. So remember, for a real vector, if A and B are real, then the dot product itself can be written as A transpose B transpose. Right? Do you agree? So if they are complex, right? So if A and B are complex, then what you do is you take A, it's still a bunch of numbers, so it's still a column, but you now take the adjoint B. And that in fact would in fact be A dotted into B, but now you take the complex conjugate of all the components of A, and that is in fact what we are writing over here is A I star Bj. Remember, my bar is the same as my star, and then you sum over I and j. Good. Very good. Okay. So let's now do linear operators. So we do need to build it up sequentially. You do cats, you do graphs, and now we're going to do linear operators. How do we use what we've done so far to build up? Oops. Okay, so now we do linear operators. So we have x and on gamma. Now I can use the same trick that I just used when I took the inner product. So let me write that down. Alpha gamma is sum over gamma alpha I gamma. Okay. So this is basically the completeness relation. So I'm going to do the same thing here. So I write x times identity times gamma. And of course, I'm not doing anything really deep here, just put the identity here. But now I'm going to use completeness. And that means I will insert x, I, gamma. And what that means is I now have, instead of x directly acting on gamma, x now acts on my orthonormal basis. Summed over this weight, the weight is given by the projection of gamma on the ith basis, which means x gamma is now equals to this guy, right? So it's now actually j, that's this j here, and then cj is given by this. So it's actually j x I gamma. So there's now a double sum. There's a sum over j over the basis, but there's also a sum over I. Okay? So now what we see is the connection between matrix multiplication and linear operators. So what is this? So if I view Ix, let me make sure I write it in the right order. Ji as x hat ji, where this is the row number and this is the column number. Then I can write this guy in terms of a square matrix. Okay, so I get 1x1, that's the 1, 1 component. This is a row, right? So everybody now is 1x2, everybody is 1 here, 1x3, all the way to 1xd. Take out the 3. All the way to 1xd. Okay. Second row will be 2x1, 2x2, and then 2x3, and so on, all the way to 2xd, and so on, until you reach the d row. This is dx2, all the way to dxd. So these are the diagonal components of your matrix, 2, 1, 1, 2, 2, and all the way to dd. These are the off-diagonal terms. When these two numbers are not the same, those are the off-diagonal terms. But this is a d by d square matrix, as you can see. But you've already seen this guy. I gamma is just a column, right? You can just write that as a column. So I can just write this out as the sum over the basis, j and I. And now if I view this as a matrix, it will be x hat j I, and it will be summed over the components of the gamma in this representation. So what is this? This is nothing but the matrix multiplication of x in this representation. So let me just write this down. This is the representation of the abstract linear operator in the basis that I have chosen. And so let me write that down. This is now the matrix x hat. Again, is the representation of the operator x in this basis, and then acting on the column, which is again the representation of the cat gamma in the same basis. When I add them, is now the j component. Okay, there's a sum over I. Then I can erase the I. Right, because now I've absorbed the I as a matrix multiplication. Right, so this is in fact, let me just write this down. This is matrix multiplication. Matrix x hat acting on column gamma. But this is where matrix multiplication comes from. Right? So the theory of linear operators is in fact the abstract version of the matrix multiplication that you learned when you were an undergraduate. So we now have a scheme because you notice, I've not assumed anything about x or alpha or gamma, any of these things. It's just completely abstract. Even the vector space, I've not really specified what the context is. But it can be anything. It's just a bunch of rules. As long as your vector space is a vector space, these rules will follow. Right? So gamma, so remember gamma is arbitrary. So that means I can just basically take out all the gammas here. I can take out all the gammas here. And I can just tell you that x in this basis is just given by the sum over I and j, x, I. That's it. I don't need the gamma, right? Because it's true for any gamma. So if I add gamma, it will just give you another cat gamma here. But what I've shown all that doesn't really depend on the specific gamma. So this must be, in fact, the expansion, let me put it this way, the expansion of x in this basis. So this is the explicit construction of any linear operator in this basis. So let me just go through it one more time just to make sure we understand. If you give me a basis, there's no problem getting the bra, it's just the adjoint. But this guy, what is that guy? Right? Remember that this guy can be computed, provided you know what x is. Because this is just saying that all I have to do is to add x on the ith basis. Right? I'm assuming I know what x is, so I know what it does on every vector. So I can compute this guy, and then just project it on the on the jth basis vector. Right? So let me just write it down here. X on I, and project j. That's what this means. So I can suddenly compute this, and this is called a matrix element. Matrix element of x. Right? This is what this is called, the Ji matrix element, so to speak. But now, if you believe this result, it means that I can construct a matrix, a linear operator by specifying the matrix. Right? So again, this is x hat ji is the j row I column of the matrix representation of x. So I can write it in terms in a short form like that. J x hat j I sum over j I. And so just like in the vector and the bra case, the cat and the bra case, when I give you the components of all the orthonormal bases, I have specified the bra of the cat. Likewise, if I know x, I can compute this. I can go backwards and I can say that I can specify a linear operator in a given basis by simply giving you a square matrix, whatever I want, right? As long as I give you a square matrix, I can plug it into this formula and use it to define x. So x, in other words, x is fully specified by x hat. Okay, again, all the information, because these are just my basis, all the information in an abstract operator, once you have chosen a basis, is given in this x hat, in this matrix. So that's what I mean here. But now, it's easy to construct the adjoint. I know I'm out of time, but let me just write that down. So now, finally, you can see how do you construct an adjoint. It's actually very easy. So if x is given by that expression over there, I can associate, remember these are just numbers, complex numbers. I can associate it with this or with I if I want. It doesn't matter. But let me just associate it with this. So this is like, remember, this is like alpha, beta. Alpha, beta. So if I want to pick the adjoint, this is where your homework comes in. This is why I give this kind of homework problems, because if you step through my problems, you would see the steps that we take to build up all this structure. Okay, so I really recommend doing the homework. Actually, start it early so that you can understand what we're trying to do here and follow along easier. So in the homework, you prove that the adjoint of this guy is just beta alpha. Okay, and so now we can do the same. We've constructed x explicitly in an orthonormal basis. So when you pick the adjoint, you just take the adjoint of every term. X hat, ji, j, I, alpha, beta. So what do? You do this cat become a bra. This guy becomes J, and you now have the complex conjugate of this guy. Okay? But remember, these are dummy variables. Okay? J and I are dummy variables. I can call them whatever I want. So in particular, I can swap them. As long as I swap them consistently, right? If I swap I with J, I better swap J with I. So now I get I, J, I get J, now J become I, so you become I, J, star. Okay. Oops, I'm sorry, I. So if I compare, previously I had Ji, now I get back Ji, but now I have, this is the Ji component, this is now the Ij component, but I take the complex conjugate, right? So this guy is in fact the matrix X hat with the matrix adjoint Ji component. Okay. Why? Because again, X hat adjoint is transpose complex conjugate. When you transpose them, you get Ji is swapped. The row becomes the column becomes the row, so Ji becomes Ij. Okay, so row is swapped with column upon transpose. Okay, and the complex conjugate is exactly this guy. So now you see that X hat adjoint is in fact represented by, in this basis, X adjoint, the abstract operator, is in fact represented by X hat, its representation, matrix adjoint. That's why the notation is the same. We use dagger, otherwise you have to introduce many symbols for the same thing, essentially. Okay. Any questions for me? You have a question? Yes.
Excuse me for the Xij. It's just a complex number. So why?
Yes.
When you say that when you take a conjugate, it becomes the row, which is means watching the row and the column.
Yeah. So
I don't
right.
understand.
So you're asking the following. I think you're a little bit confused, which I understand. This is a number, right? That's what you're confused about. But yet I say I'm swapping rows and columns. But what I mean by that is if I view this as a matrix whose Ij component is this guy, right? This is the Ij component. Ij component of this guy here. This you understand. So when I say I take the matrix adjoint, that's why I put a parenthesis here. I view this as a matrix first, I take the transpose, I take the complex conjugate, then I look at the Ji component. Okay? But because I took the transpose, let's do it step by step. Okay? So if I have a matrix, if I take the transpose and then I take the if I look at the Ji component, do you see that this is equal to the same matrix, but it's the Ij component, right? Remember?
And also.
Yeah, that's why I put transpose first, right? I put transpose first, one operation at a time. Yeah. So again, the matrix, then I look at the component, Ji. This is the matrix, I look at the components. But because there's a transpose, I'm swapping basically Ji, because row becomes column, column becomes row. Just so you understand. Then I take the complex conjugate, right? One operation at a time. But complex conjugate applies to every component, right? So if someone commutes, I can just take transpose becomes adjoint, and then I can just take the complex conjugate like that. So that's what's happening here. Good. Other questions for me? All right. If not, see you guys on Friday.